Hi everyone, my name is Shabina and I'll be talking about nonlinear optimization. So what we'll be covering in this podcast. So what we'll be looking at, what is nonlinear optimization? We'll be looking at one variable nonlinear optimization and n variable optimization. We'll also be looking at a conclusion from my investigation just to sum up what we found, what our findings and results were. So how do programming problems arise and why do we need them? So we have maximization and minimizations problem almost on a daily basis. With the applications in industries, just on building sites. So things like maximizing the area covered by a batch of cement or by building blocks in order to minimize the cost. A good example is how we maximize profits and minimize risk in stocks and shares in portfolio risk management. That's a very good example to see why we need maximization and minimization problems. So what is nonlinear optimization? Nonlinear optimization is when we're using this is our standard output for a minimization problem, a standard setup for our minimization problem. We have an objective function f of x, which for it to be nonlinear, it has to be a nonlinear function, so the variables may depend on each other. It's not a linear problem. And in this investigation, we have only been looking at unconstrained nonlinear optimization, meaning that we have no constraints on our objective function. So looking at a one variable optimization, we only have one variable in the objective function. So whether it be x or y or x1, it's only one variable. There are two different methods that we can use to find the minimum. One of the methods is known as the direct method, and it only uses the function value. So you don't actually work anything else out. You only require the function values. The second method that we can use is the gradient method, and this uses the derivatives, whether it's the first derivative or the second derivative. And in this investigation, we will only be looking at the gradient method itself. So looking at the optimality conditions for the gradient methods, what do we need to ensure before we can apply a gradient method? So the first condition is that the first derivative, so f prime of x, has to be equal to 0. This is to make sure that we are at a turning point. So it could be a minimum point or a maximum point, but we have to make sure at that point f prime of x is equal to 0. That is where the minimum lies, or the maximum lies. And the second condition is this is how we determine whether it's a minimum or a maximization problem. The second derivative has to be greater than 0. That ensures that we are at a minimum point. So the first condition that we're going to be looking at is called the secant method. The secant method is derived from the equation of a straight line, so y equals mx plus c, or from the Taylor series. It's an iterative process, so it draws lines on a graph in order to come closer to the minimum, and it uses that formula to find the minimum, to find the next iteration. So the way the algorithm works is you pick 2 points, x0 and x1, and you repeat the formula. You put it into the formula to find your next point, x2, and then so on to find x3, and you repeat until the gradient is equal to 0. And that ensures that we are at the minimum. So how the secant method works is if we look at the graph, we can see that if we have an initial point x0 and we have an initial point x1, we can draw a line which will cut the point at x2. So that is now closer to the minimum than x0 was and x1 was. So we are getting closer and closer to the minimum as more iterations that we do. So the advantages of the secant method is that it only uses the first derivative. So we don't have to calculate anything else apart from the first derivative. And another main advantage of the secant method is that it will never fail. We'll see that some other methods that we'll be looking into can fail. The disadvantages of the secant method is that it may not necessarily converge to the minimum. It could just stay at one point and stop. And we have no guaranteed error bound for the computed iteration. So what that means is that we don't know if we're shooting too far out or whether we are too close to the first point that we had. The second method that we'll be looking at is called the Newton-Ralphson's method, or the Newton's method. And this is again derived from the Taylor series and uses the formula in this text box here. We pick a single point x0, and then for all I, which is 0, 1, 2, 3, we use that formula to find the next point. And we repeat again until the gradient is sufficiently small or equal to 0. The way the Newton-Ralphson method works is it uses the first and second derivative, And it's an iterative process just like the secant method as well. And as we can see in the graph, how the line is getting closer and closer to the minimum. So as we can see that it's moving closer and closer with each iteration towards the minimum. So the advantages of the Newton-Ralphson method is that it is the fastest converging method that we have to find the solution with fewest iteration. It works on the assumption that it works quadratic, that the minimum lies at a quadratic, so it finds the minimum a lot quicker using that assumption. The disadvantages are it requires the first and the second derivative, so we have an extra calculation to do. And if the second derivative is 0, the method will fail because you cannot divide by 0 in a fraction. And the third point is that we need the initial points x0 has to be close to the minimum, because we'll find that if it's not close enough to the minimum, the Newton's method will not converge to a minimum. It will go infinitely far away from that minimum. And you can use a method known as the safeguarding of the Newton's method, and more information you can find that on my investigation, and outlines how you can use that in order to remove this disadvantage. And this is where it fails. The secant versus the Newton method. So we've seen a lot of advantages and disadvantages for each of the methods. So it again will depend on the function type that we have. So if the function works for the Newton's method, it is the most efficient method that we have there. However, if the Newton method doesn't work, it will fail. We cannot make it work. When using the Newton's method, we need to pick a point which is very close, whereas the secant method, we don't need to be so close to the point. So again, if we were to look at which method just finds the answer most quickly, it will be the Newton's method. So what is n-variable optimization now? So n-variable optimization has an objective function which has more than one variable. So it's denoted as f of x is equal to f of x1, x2, x3, and so on. So f of x is considered to be continuous. So that means we can find the first derivative and second derivative and so on. So we can also solve, again, like similar to the first and to the one variable optimization, we can solve using a direct or a gradient method. There are many different gradient methods to find the minimum. Some of them we'll be looking at, which is known as the steepest descent, the Newton's method, and the Quasi-Newton method. So we need to know a few things before solving n-variable optimization. So first of all, we denote the gradient, which is the partial derivatives of the objective function, as g, and it's defined as this text box here. And the second partial derivatives that we have is known as the Hessian matrix, and which is defined as a square matrix that has all the partial derivatives in it. So the optimality conditions for n-variable optimization is that the gradient, just like the one variable optimization, is the gradient needs to be equal to 0. So this is to make sure that we are at the minimum. And the second optimality condition is that the Hessian has to be a positive definite matrix. Now we have to check this condition for all the methods that we use, and we can use the determinant to find the eigenvalues in the Hessian matrix to ensure that they are all positive. Or we can use another method which is known as the Cholesky factorization. So all the gradient methods for solving n-variable optimization uses a line search technique. Now what is a line search technique? A line search technique is an iterative process to find the minimum. So a line search consists of two parts, which is a pk, which is a search direction, and a step size s, and it uses that formula in there. So there are two different types of line search techniques, which is known as a perfect line search and a weak line search, where the perfect line search is a calculated value of s, and a weak line search uses any value of s. So there are three conditions on the line search to ensure that we are working towards a minimum. So the first condition is called the sufficient decrease, and this is to ensure that the step size is not too big, so we're not shooting too far out. The second condition is known as the curative condition, which ensures that the step size is large enough, so to make sure that we are actually moving closer to closer to somewhere. And the third condition that needs to be satisfied is known as the strong Wolfie's conditions, and this is to ensure that we are actually in the direction of the minimum, so we are actually moving closer to the minimum and not just standing somewhere or maybe moving too far away, or moving away from the minimum. So we have to ensure that we are going towards the minimum. So first method we're going to look at is the steepest descent method. This is an iterative process that uses the line search technique, and the algorithm is as outlined. So you start with an initial point x0, you find the gradient, and you find pk, which is denoted as minus of the gradient. You have to make sure that pk transpose and gk multiplied by gk is less than 0. This ensures that we are in the direction of the descent. We have to find a new point using that formula, and we have to calculate the step size s. So this is for a perfect line search. We have to calculate the step size s by using the first derivative. So we have to repeat until the gradient is equal to 0. That's to make sure that we are at the minimum. So the advantages of the steepest descent is the cheapest method available. It requires minimal calculations. You don't have to work out the second derivative. You don't have to work out anything else. So it is the cheapest available method. It works easily with larger models. So if we have a model with more than 5 variables, more than 10 variables, it will be the quickest method that will work efficiently. The method that works, the method works. That's one of the key points about it. It will never fail. There's no way that the method can fail, even with any starting point or with any number of variables. So the disadvantages is that it will take more calculations. It's not the efficient method over all the available methods out there. So it will take more iterations to come to a solution. The second method that we're going to look at is the Newton's method, and it's an iterative process, uses a line search technique, and uses the partial second derivatives. So it uses the Hessian matrix. It starts with the initial point x0. You find the gradient, you find the Hessian, and you have to do a calculation to ensure that the Hessian is positive definite, again by either using the eigenvalues or the Cholesky factorization. Then you have to find the pk by using the inverse of the minus inverse of the Hessian multiplied by the gradient. And you find the new point, and you repeat the process until the gradient is equal to 0. Advantages of the Newton's method is that it converges faster than the method of steepest descent. And this is because the steepest descent is thought of as an approximation of the Newton's method. The disadvantages is if the initial point is not close to the solution, the method will not arrive to the solution. So we have to be close again to the minimum before we can start the method. A second disadvantage is that we have to calculate the Hessian and the inverse of the Hessian, so it will take longer with hand calculations. The third method we'll be looking at is the Quasi-Newton's method, and it comes directly from the Newton's method, but it uses an approximation of the inverse Hessian. So we're going to denote that as g of k. So the algorithm is outlined by starting with initial point x0. You find the gradient, and you let the inverse Hessian equal the identity matrix. Usually that's just what we start off with. So you find pk, but it's equal to the minus of gk multiplied by lowercase gk, and you find the new point by using that formula. And we have to calculate these components. So we have to calculate xk plus 1, gamma of k, and delta of k using these formulas. And we have to find gk plus 1 by using this formula here. And with this, we've got two methods for the Quasi-Newton. First is known as a DFP, which stands for the David Fletcher Powell. So that's a type of Quasi-Newton method. So that's one of them, and it uses this formula. And again, we repeat this process until the gradient is equal to 0 or sufficiently small enough. And the second method is the BFGS, which stands for the Broyden, Fletcher, Goldfrapp, and Shano. It uses the same process again as the Quasi-Newton, and we take these components and we put it into this formula, and we repeat it until the minimum is found. So advantages of the Quasi-Newton method is we do not have to invert the Hessian. So we don't have to find the inverse of the Hessian matrix. We use an approximation. The second advantage is we don't have to check if the Hessian is positive definite. We don't have to keep checking that because of a condition known as the Quasi-Newton condition. So what that means, it will always be a positive definite Hessian matrix. The disadvantages is we have to calculate the Hessian matrix, and it requires more hand calculation. The steepest descent versus the Newton method versus the Quasi-Newton method. We can apply perfect or weak line searches to all of these techniques, and they all have their advantages and disadvantages. Some methods, such as the Newton methods, work better than the other methods. We've run, in my investigation, if you look at the report, we can see that the Newton method performs better in some of the functions than any other method did. Again, this will depend on the function and the initial point you start with, how many iterations it would take. So we can't actually come to a conclusion one method is better than the rest. In reality, with active research, because of this problem, and it's still going on today, the most efficient method that they have seen is the BFGS, so the Quasi-Newton BFGS weak line search, and it is the most efficient method so far that they believe. So thank you for watching, and if you have any questions, I'd like to hear them at the Viva. Thank you.